Welcome to Math 408, L functions and sphere packing. This is lecture 32, and so this is going to be the continuation and conclusion of the Gauss circle problem. So just quickly review from where we were last time. The Gauss circle problem talks about the standard integer lattice Z2 and asks, if you consider a circle of radius r, how many lattice points do you have inside the circle? And there are explicit formulas for it. The question is always, of course, how easy is it to work with these? Whenever you see a floor function or a ceiling function, you should be concerned. There are a lot of really bad proofs of wonderful results in number theory that come down to using the floor function incorrectly. And so these proofs are not salvageable. It is hard to make stuff like this work well, which is one of the reasons why there is such efforts to get a better estimate of what the error term is in our counter. Right, so we talked about the different issues. The main term wasn't too bad to get. It's going to be pi r squared. And one of the questions was, how many points could we actually have on the boundary? And this was a great example of how data can help lead the way. And it was quickly noted that the radius corresponding to the smallest circle that had a given number of points on the boundary seemed to always be a multiple of 5. There didn't seem to be any obvious reason for that. If anybody can find one, I would love to know, and I will make that extra credit. We did see how, well, when the radius is 0, this is a degenerate case, so let's ignore that because the 4 points on the axes coalesce into 1. When the radius is 1, you had 4 points, and then everything else was congruent to 4 mod 8, and we saw that this was because of a symmetry. You could flip x and y, and you could add plus or minus signs to each. So the homework problem is to prove or disprove there's a positive alpha such that infinitely often there are order r to the alpha points on a circle of radius r. And so I took the points in the data table and just made a list in Mathematica. So the first entry is the radius, the second entry is the number of points. And then I made a new list where I just took the log of the previous. So you can apply the function log to the entire list immediately. And what's nice is Mathematica has reached the point where a lot of functions that you want to use have been built in, including finding the best fit line. So rather than programming the method of least squares or any of that, I can just say fit, and here's my data. I want to use the functions 1 and x is the variable. And then I plot the data and the best fit line. Anybody know how I was able to plot the best fit line without knowing what the best fit line was? How can I have coded this without knowing the answer? So the answer is I obviously ran the code first, found what the best fit line was, and then just plugged those numbers in here. So if you look at this, this seems to be a pretty nice linear relationship that it looks like maybe an exponent of 0.28. So maybe it should be safe to try to prove at least a quarter. So for homework, prove or disprove that there is an alpha such that infinitely often there are order r to the alpha points on a circle of radius r. The data could be misleading. Maybe there is a completely different approach than doing this. Or maybe the data is suggestive, that maybe it's highlighting a phenomenon. There was something that we saw over here that was valuable. We talked briefly about the points, about the proof. We would take each lattice point, and the furthest another lattice point could be, the closest another lattice point could be is 1, could also be square root of 2. So we looked at circles of radii differing by root 2, and we could do inside, outside, do estimations like that. And we were able to establish the main term was pi r squared, and the error term was of order r. All right, so new stuff for today. So what I want to do is I want to talk about radial symmetry and how this is valuable and how we can use this. So earlier in the semester, when we were talking about interpolation, I mentioned that one of the key advances was finding a radially symmetric function that had certain desirable properties, and the sphere packing argument came down to showing that such a function existed. we're going to see a lot of interplay between geometry and analysis. And this is a 400 level course. This is supposed to show you a little bit, where does everything go? So that if you decide to continue in mathematics, you have an idea of, well, what classes might you want to take? What problems are you interested in and what techniques are useful to solve them? Or if you decide not to go further in mathematics, you at least have a sense of where things are heading. Another thing we're going to see today is the value of having multiple representations, in this case 2, for the same quantity. And frequently what it means is a quantity that we really want, that we really care about, that's very desirable, is going to be very hard to compute in the original formulation. But if we can show it's equivalent to something else which is easy to calculate, then we've made enormous progress. The next thing is the difference between smooth counting and discrete counting. In number theory, it is very hard to have sharp cutoffs. So if you want to count just how many primes there are up to x with a sharp cutoff, that's a lot harder than having a smooth weight function where maybe every prime up to x is given a weight 1, and then you have a weight crashing down when you get up to maybe 2x. Or maybe you want to crash down much closer to x, maybe x plus log x. And when you put in these weights, it's often a lot easier. And then you don't have these agonizing decisions, well, does it make it or not? Because right now, if we have a circle of expanding radius, we could go through a bunch of points on the boundary. And those are either all in or all not in, depending on the radius. The next is Poisson summation. It is an absolutely wonderful tool, and it is incredible how useful it is. Its greatest use is when we can express what we want as another sum, and in that new sum, only one term typically matters. We can evaluate one term without too much trouble. That's not so bad. It's these infinite sums that cause us headaches. Now, it is possible to apply Poisson summation multiple times, but what happens if you apply Poisson summation to a function twice? What would you get back?
The original sum.
The original sum. So one of my advisors, Henrik Ivanyac, who I will be sharing some of his notes in a moment, he actually applied Poisson summation twice in the same paper, but in a non-trivial way, because what he did is he first applied it, then he did some work, and then he applied it again to the new quantity. So it was not a triviality to do that. And then the last thing that I want to talk about is integral representations. So we have spent a lot of time in your career teaching you calculus. Everybody here has taken at least 3 calculus classes. Depending on what you've done in real analysis or measure theory, you might even count that as a 4th or even a 5th class. It would be nice to be able to use those tools. If you've taken complex analysis or taken complex analysis, that's another example of a calculus class. Well, a lot of times we have discrete quantities that we want to study. And when you have discrete quantities, the tools of calculus are not available. So you want to try to find integral representations. Have we seen any examples of that this semester? We replace something discrete with something that's continuous and differentiable.
We did that with the floor ceiling problem with e to the.
Yeah, we did that when we were looking at, we have some number n, and we want to break it up as a sum of numbers to maximize the product. And the numbers have to be positive, otherwise it's trivial. You could just run the product to infinity by including pairs of negative numbers. And so we were able to pass from a discrete problem to a continuous problem, use calculus, and then pass back to the discrete. And so we'll talk a little bit about that today. And then for Friday's lecture, it's going to be an asynchronous lecture. I'm going to post one of the talks I gave in complex analysis. I think I'm posting the 2017 version, not the 2015 version. It's on an absolutely wonderful method that allows you to approximate extremely well a large class of integrals. And we will see later today why we want to be able to do that. And the lecture is, I believe, for the most part, self-contained. All you need to know is the basics of the Gaussian. You don't really need to know, I think, too much of complex analysis. If there is, I apologize. but I want you to just get a sense of what's out there. If you are going to math grad school, you really should take complex analysis. The core classes that we advise are measure theory, complex, and Galois. If you can work in topology, that's wonderful. If you ever want to take complex and we are not offering it, let me know. I've recorded all my lectures. I'm happy to run independent studies. All right, so I am going to share some notes from my advisor's book, Introduction to Spectral Theory of Automorphic Forms. Henrik Ivanitz is a phenomenal lecturer and writer. It was a pleasure to be able to attend his classes. And he does a great job of explaining why you're able to get some of the savings you can. In number theory, we often do a tremendous amount of work to save a logarithm. For the homework problem, I asked you to find that alpha. I did a quick calculation using a result I know from number theory. And unfortunately, the result I get is something like 16 for the exponent divided by log r. And unfortunately, 16 divided by log r tends to 0, and so my result is useless. It doesn't do what is needed. There are other ways to prove that there is such an alpha or disprove that there is no such alpha. But I was just curious, could you push an elementary result in a certain way? And a lot of times as we try to do these arguments, we are right on the cusp of what we can and cannot do. As an aside, how many of you have ever read Rudin's Principles of Mathematical Analysis, also known as Baby Rudin? So there is a nice problem. Look at the sum of 1 over n. Does that converge or diverge?
Diverge.
Diverges. This is the harmonic series. What if I gave you n log n? And we'll do, n less than or equal to x. What do you think? Converge or diverge?
I think it still diverges.
Diverge.
It still diverges. If you replace this with an integral, if you let u equal 1 over, I think log n, no,
It's just double log n.
double log n. You want u to equal log of n. Is that what you said we should use?
I'm saying that when you integrate it, that's what you get.
Oh, yeah, yes. And I'm saying that the change of variable we should use is, do we have,
You just want u equals log n.
is log n, and then du would equal 1 over n dn. So we now have the integral of 1 over u du, I think. Yes. And so the integral will diverge. What if instead of having log n, I instead have log n squared?
That should converge.
Right, that converges, and now we have a 2 over here. And so
Converge.
Rudin has a beautiful section where he talks about trying to find this boundary of convergence, where it diverges below this mark and it converges above. We can keep playing this game as much as we want. And instead of doing log n, we could do n log n, log n, and then n log n, log n squared, and just keep playing these games trying to find, where will it converge, where will it diverge? Okay. So what I want to do is talk a little bit about the framework. So R2 is just all pairs of real numbers, and then it's a group under addition, and it acts by translating. So if I give you the point, 3, 4, it would send xy to x plus 3, y plus 4. So there's a standard metric, ds squared is dx squared plus dy squared, or another way of saying it is ds is the square root of dx squared plus dy squared. This is a mistake that's often made in calculus classes, is people say ds is just dx plus dy. And that is not the case. If that was the case, all curves would actually have the same length if they have the same endpoints. And so we have the standard Laplace-Beltrami operator. If you haven't seen all this stuff, this is fine. This is just bird's eye overview of a little bit of what's out there. And so this is an extremely important operator in mathematics. And we can talk about what are the eigenfunctions of this. So here, E always means e to the 2 pi I of whatever the argument is. And the eigenfunctions of this operator are going to just be these exponential functions. And when you apply d by dx squared, you're going to bring down a 2 pi I squared and a u squared. And over here, you'll pull down 2 pi I squared and then a v squared. And so there's our 4 pi u squared plus v squared. And it's because we have this written as a plus, not as a minus over there, that the minus has gone away. And so we know what the eigenfunctions are, we know what the eigenvalues are. There's a lot that needs to be done that I am completely glossing over. We do not have enough time in the course to go through all this. I'm just trying to show you a little bit what's out there. Why might this be useful for the problem we're trying to study today? So can anybody think of why these eigenvalues might make us excited?
They're kind of like a circle, u squared plus, v squared is like the circle formula.
Yeah, I mean, basically, if we take u and v to be integers, not just real numbers, then u squared plus v squared is the length of the lattice point uv. And so maybe if we have some understanding of the eigenvalues, maybe we can count how many eigenvalues there are up to a certain level. And that will give us information about lattice points. So that we can actually convert problems from, say, geometry to problems in analysis. So there is the well-known Fourier inversion pair. Does anything look different from this from what you've seen before?
There are two variables now.
So one is that there's two variables. There is another difference from what we've seen before.
It's positive instead of negative.
Yes, so the signs have been switched. If your function is even, it makes no difference. But this is just, you've got to be very careful that depending on what book you're looking at, there are slightly different conventions as to how they define things. I am not going to comment on the plus sign or the minus sign. To me, the real one is, do you have the fact of 2 pi in the exponential? And there are some books that don't have that. The 2 pi makes the Fourier theory leading up to Poisson summation nice, but there are other situations where then you have 2 pi's in formulas. You can't get rid of 2 pi everywhere. And so physicists sometimes choose a different normalization because they want other formulas not to have the 2 pi. All right, so one way to view what's going on is through a theory that's called invariant integral operators. So we have some operator L, and it has some kernel K, and we get a new function. So we have a map from functions to functions, and we integrate over all of our to K of ZW times F of W dW. So when we do the integration, we're left with a function of Z. And the question is, what can we say about such operators? What would it mean for F to be an eigenfunction of such an operator? If I give you an operator, if I can give you a nice geometric definition of it, is there a nice interpretation for what K should be? So we've mentioned that the group that we're looking at is the group of translations. And so what we often want is we want our integrals to be invariant under certain transformations. So when we go back to over here, if I replace W, if I change w to w plus some vector v, is the integral unchanged? If I do a translation like that. And so it turns out that if we want our if we want to replace z with z plus something, it turns out that if the kernel only depends on the difference, then our resulting function will be g invariant. So we can replace z with z plus v, and it will not really change. And the reason is, here, if all that matters is the difference between the points, as we go through everything is going to mutually cancel. You can directly show that the exponentials have wonderful properties, and it turns out there's advanced theory connecting everything. So we're going to look at radially symmetric kernels. We're going to look at kernels that depend on just how far you are. So what is unfortunate about this notation over here?
K sometimes takes multiple variables and sometimes one.
Correct. So K takes two variables, except when it's clear that it takes one variable. And so you get to the point where you look at these and you understand, am I evaluating K at the radial distance from the origin, or am I evaluating K at a pair? And then from that, I figure out how far away I am. So we care about kernels that only depend on the radial distance. And when we looked at the definition of the Fourier transform, this is the Fourier transform in x and y coordinates. Well, as soon as I tell you I have a function that only depends on the radial distance, what should you immediately be thinking of? So imagine you have a function that only depends on the radial distance.
Can we use a one variable Fourier transform?
To some extent, yes. What kind of coordinates should you be thinking of?
Polar coordinates.
And that's the whole idea, is that we rewrite the Fourier transform in terms of not dx dy, but in terms of dr and d theta. And the theta integral becomes very easy to do, and you're left with the following integral. Has anybody here ever seen the Bezel function before? So the Bezel function is one of a multitude of special functions that appear throughout all of mathematical physics. And because they appear so often, a lot is known about them, a lot has been tabulated about them. And so I'm just checking something right now. It turns out we can replace our integral with basically k of r times the Bezel function when we're applying this to the exponentials. And that's because we are assuming our kernel only depends on the radial distance. What's nice now is this is a problem that could be studied quite well for very specific choices of k. These integrals might be possible to do. So the Bezel function, it turns out a lot is known about it. How many of you have ever heard of Gradstein and Ristic? Oh, I do have it, okay. So I'm going to stop the share and turn on video for a second. So I went through 4 majors when I was an undergraduate. I was a math major, physics major, combined major, and a double major. And one of my physics professors told me that you should always carry a table of integrals on you. And so this is a small table of integrals that fits in your bag without too much trouble. I don't know if this is at all visible with the lighting. It's not too bad. Here's Gradstein and Ristic. And you can hopefully see a little bit of the difference between the two. Sometimes when I need exercise and I'm just walking around the campus, I just throw this in my backpack for weight. It is a wonderful, wonderful book. It is extremely detailed. I have no idea how much of this is actually visible. But what's nice is we are now in the 21st century. And so things are very different than when I was a student. In particular, it has a Wikipedia page. And more than just having a Wikipedia page, you can actually download the book for free. So part of your homework this week is to download this book. I did not officially write this on the homework list for the week, but just when you hand in your homework, just say that you downloaded this book. You should have a copy of it. And you're given that you can download a copy for free. It is absolutely wonderful. There are lots of books. This is one of the most famous. Another one that's very famous is Abramovich and Stegan. And again, homework problem is to download this as well. So this is the easiest, I think, 20 points you could ever get on a homework assignment. What's really nice is
Wait, it's both books?
Yes, you have to download each book.
Okay.
So you should have both books. It takes a while to learn how to use these. With the era of Mathematica and all of the web resources, these are less useful than they were in the past. One of the greatest challenges when you have systems like Mathematica or books like this is converting your problem to a form that can be recognized. There's a famous story that when Kepler was working out his results on planetary motion, he was studying Mars, and he thought it might be an elliptical orbit, but unfortunately what he proved was not an ellipse. It turns out it was the equation of an ellipse, but not in the standard way that he was familiar with, so he didn't recognize at first that he had actually shown it was an elliptical orbit. This is the same with so much algebra, is trying to find the right way to look at things. And if you can find the right way to look at things, the problem often becomes trivial. It is a challenge sometimes to use these books and to figure out how do I change variables to make what I'm looking at equivalent to the problem at hand. And I think at one point in the semester I showed you the Rubik's Cube, where if you rotate it 45 degrees, now all of a sudden it's a standard cube. But if you try to do it directly, it's going to look different. So these books can be a little bit of a chore to use, but it's the same with Mathematica, that sometimes it doesn't recognize that it's something that it knows. Okay, this is a capstone class. So one of the things of a capstone class is to try to show how those courses that we required you to take earlier matter. And so I'm going to go back to linear algebra, to what is one of my most favorite results in the course. At the time when I first learned it, I had no idea why it mattered. It's the eigenvalue trace lemma. So the trace of a matrix is the sum of the diagonal entries, and lambda is an eigenvalue of A if there's a non-zero vector such that AV equals lambda V. And the eigenvalue lemma is that the trace of A is the sum of the eigenvalues of A, counted with multiplicity. So any thoughts on how we would prove this? Or if you can't prove it in general, any special cases where you can prove it?
The matrix is a diagonal matrix, and I
Good.
can prove it.
Good. So how would you prove it if it's a diagonal matrix?
The eigenvalues are the diagonals.
The eigenvalues of the diagonal entries, we're done. Okay, so this should remind you of the arguments we did when we were looking at SL2Z. And we were looking at trying to represent any matrix as a word in T and S. And we first said, well, let's first assume that the lower left entry is 0. And we saw that we could do that. So given the success of diagonal matrices, why don't we just show that every matrix can be diagonalized? Can we do that? So does anybody know the result as to whether or not every matrix can be diagonalized? And by diagonalized, I mean the following. So we say A is an integral that S A inverse. So do you think every matrix can be diagonalized?
Well, you need determinant, positive determinant.
Why do you need positive determinant?
Because otherwise, well, every diagonal matrix has positive. Oh, actually, no, it doesn't. Never mind.
No. Nope.
What if you had a 2 by 2, a 2 by 2, 0, 1, 1, 0,
0, 1, what else?
1, 0? Is that's not diagonal. Diagonal.
What are the eigenvalues of this matrix? So you would get lambda squared minus 1 equals 0, right?
Mhm.
So we get lambda equals plus minus 1. Yes? So this matrix is diagonalizable. So as a nice exercise, diagonalize this matrix. How do I know it's diagonalizable immediately? Well,
You could find the eigenvectors. They're pretty.
yeah, I was about to say, it may not be diagonalizable. I've got to be careful. I've got to make sure that I don't have a repeated eigenvalue.
No, you're good.
But I'm good because it's lambda squared minus 1, not lambda minus 1 squared. So I have two distinct eigenvalues. And so I can get V1 and V2. And then the matrix S involves V1 and V2. It may be just putting them in like this, or maybe the inverse of that. It's something like this. So this was not a bad try, but this matrix is diagonalizable. We could modify it a little bit, though.
What if we tried?
Yeah, what if it were
Yeah.
0?
So
So
now,
then it's, then it's,
That's not invertible.
you get lambda
violates
squared
our-
equals 0, and you get a double root.
mm,
And in fact, it really doesn't matter what we choose for the diagonal. Anything we choose for the diagonal, if we chose 8, that would be fine as well. The reason I'm choosing 8 is I can make the 0 to 8 without any trouble. So any matrix of this form can't be diagonalized. So as a nice exercise, prove this. Prove that there is no S that works. So unfortunately, we can't just say diagonalize the matrix. Any thoughts what we could do then, since diagonalizing won't work? Oops.
if it has determinant, no, because then you just flip it. Never mind.
So diagonal might be too restrictive of a class. Not everything can be diagonalized. what is weaker than diagonal, but you would still know the eigenvalue trace lemma for these matrices?
Triangular, maybe?
Triangular. So it's trivial if A is upper triangular or lower triangular, but we don't seem to like lower triangular. If it's upper triangular, the eigenvalues are still the diagonal entries, and the trace is still the diagonal entries. So now what you do is you prove that any A can be brought into upper triangular form by conjugation. And wow, I have no idea why I wrote U and not T. Oh, okay, now I know why I wrote that. U for upper triangular. And so this is one way to prove the eigenvalue trace lemma. So it's a nice exercise to prove that any matrix by conjugation can be brought into upper triangular form. I'm not going to require that, but I strongly urge you to see if you can prove that. And then the final result you need is the trace is not quite commutative. The trace of AB is not the trace of BA, but it is cyclic. The trace of ABC is the trace of BCA. So the trace of SA S inverse is the same as the trace of A. And again, that's another nice thing to prove. And this gives us the eigenvalue trace lemma. It relates the trace of the matrix, which is the sum of the entries, to the sum of the eigenvalues, which is a spectral quantity. And it turns out that there is an analog in what we are doing. I'm not going to go through the details because it's just going to get us to Poisson summation, but I've just pasted the pages if you want, where you talk about what does it mean to calculate the trace of an operator. And here you should recognize that this is something very similar to what we've done before. We've done a periodic sum. We did this when we were doing Fourier analysis. We took our function, and then we had our little function f, and then the big function was looking at the sum of little f of x plus n, where n ranged over everything. Now we're just ranging over all points p. And this means we're integrating over a unit square, and a unit square has area of 1. So there's a lot of times where there's factors of 1 that are going on here. And you get in operator theory that the trace of L is going to just be the sum of Kmn. And then you can also do it with a Fourier analysis spectral decomposition, where we basically say a nice function can be written in terms of the Fourier basis, and then the trace is given by the sum of the eigenvalues, and we know what they are from looking at the functions phi and everything, and k, and you basically get the Poisson summation formula. So this is another way of getting to the Poisson summation formula. So you can interpret this as a generalization of something that you've hopefully seen before, the eigenvalue trace lemma. Why do we care about something like this? So here's an improvement to the Gauss circle problem. So we're going to assume that we have some radially symmetric K, C0 infinity. Has anybody seen that notation before?
Continuous functions on that interval.
More than just continuous.
They go to 0 in the limit, maybe? No.
Is it infinitely differentiable?
So it's infinitely differentiable. That's what the infinity is.
Is it a uniform continuity thing?
I think the 0 is compact support. It's been a while since I've done this analysis like this, but I believe this is compactly supported infinitely differentiable functions. And so we have basically through the Poisson summation formula, the sum of RL KL is the sum of RL KL tilde, where it's not quite the Fourier transform because we are using the fact that our function K is radial to replace the two-dimensional Cartesian integration dx dy with a d theta dr. And you have this new integral against a Bezel function. But the counts are coming from how many times you have integers summing to L. The sums of their squares is L, their distance is L. And you can see now why this is going to be useful for the circle, for the Gauss circle problem. Imagine the function KL was 1 inside the circle and 0 elsewhere. Well, then this would just count how many lattice points we have inside the circle. And so we can't quite do that. We need our function to be smooth, but because there is a finite separation between all lattice points, we can actually have the function K crash down hard. So I'm not going to go into the details here. I'll just leave up the slide. But basically, by doing some analysis of the Bezel function, there is a way to approximate this integral and get some cancellation. And this lowers the exponent down to 1/3. And before you get too excited, the notation we're using is that we are doing a circle of radius square root of x. And so there would be a circle of radius x, if r equals the square root of x, then this would become r to the 2/3 in terms of what the radius is. So we're not getting below 1/2. You just have to be careful as to how we're looking at things. Right. So what I want to end with is just talking a little bit about the power of integral representations, because that's the key ingredient in making progress on the Gauss circle problem, is we converted it to a count with a nice function, and then we were able to apply some analysis to this. So let's apply this to one of the most important functions that we use that is a discrete function, the factorial function. So we've seen that we can generalize the factorial function through the gamma function as the integral of e to the negative x, x to the s minus 1. And it's convenient sometimes to view it as dx over x, because if I change variables, if I replace x with 5x, the 5 cancels in the numerator and the denominator. This measure is invariant under the change of variables by rescaling. Okay, so the gamma function satisfies a functional equation. Gamma of s plus 1 is s gamma of s. And from this, we get the beautiful result that gamma of n plus 1 is n factorial. So I love ending sentences with a factorial and a pair of proofs. So if we want to understand n factorial is just this integral. So we reduce the problem to studying this integral. Any thoughts as to where this integral is largest? Or how you would at least find where it's largest?
Where the derivative is 0.
Yeah, where the derivative is 0. And so we look for the critical points. And so if we take the derivative of x to the n e to the minus x, after a little bit of calculation, you'll find that it's at x equals n. All right, so if we plug in x equals n, we get n to the n e to the minus n. Oh, that's looking a lot like Stirling's formula. Stirling's formula says n factorial is about n to the n e to the minus n square root of 2 pi n. Well, now that we know that the action is happening at x equals n, one way to attack this problem is we could actually rewrite it and write x equals nu and try to pull out some of that independence. And if we do that, we'll get n factorial is n to the n plus 1 integral u to the n e to the minus nu. And what's nice about this now is we have tremendous decay here. And you can similarly see that the integrand is largest at u equals 1. So what I'm going to do is I'm going to try to approximate the integrand by looking at what goes on near 1. And I'm going to go 1 over n in both directions. So if I take u to be 1 minus 1 over n, where we get 1 minus 1 over n to the n, well, that's converging to 1 over e. If I had taken a plus sign, if I had taken 1 plus 1 over n, it would look like e. Now, if I look at e to the negative nu, at the smaller value, it becomes e times e to the minus n. Oh, the e cancels the 1 over e, that's nice. And at the other side, it becomes e to the minus n over e, and that e cancels this e. So in this range, our integrand is actually looking like e to the minus n. And the interval is of length 2 over n. Whoops, the 2 should be upstairs. And so we get that it should look like 2 times n to the n e to the minus n. So actually, let me quickly stop the share. I will switch to the so let me just quickly change this. This should be a 2 upstairs. And so we should have a square root of 2 pi. Well, square root of 2 pi is definitely more than 2, so that's not so bad. We're missing a square root of n. and we don't have quite the right constant. This is also not officially a lower bound. I just looked at what was happening at the left endpoint and the right endpoint. And I approximated things. So my question is, can you do better? Can you prove that this is a lower bound? What if we went a little bit further? Can we get a more accurate answer? And the answer is yes. And so that's what I'm going to have you watch for Friday. This is a video from complex analysis that I taught a couple of years ago. It's the method of stationary phase, or Laplace's method. It is incredibly useful for evaluating and approximating integrals like the one that we have over here. And it gives you, the main term plus a very small error. And you need some parameter going to infinity. Here, the parameter that's going to infinity is, of course, n. So I'm just, posting the homework problems. So I've added, one problem officially, prove or disprove that there is an alpha, such that infinitely often they are order out of the alpha points on a circle of radius r. I'll try to remember to download the 2 books as officially problems posted. Please make sure to do that. These are just really useful things to have on. Okay, any questions? Okay, have a great weekend, and I will see you on Monday.